Hi, this is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. In the course of vibration control, in this module we are discussing about the design considerations in the material selection for suppression of the vibration, because this material is basically providing the damping feature in that. So, in the previous class we discussed about the sensitivity analysis, because we know that when we are trying to consider the damping feature, and if any changes are there because of, say, the type of loading or because of the environmental conditions or because of, you see, some specific features which are being added during the running time of machine, then how to relocate or how to redesign the damping features or the the material selections in that. And even you see, if there is no change in that, but even you see we just want to further refine, like you see, as I explained in the previous lecture, that if you are considering the the automobile sector, then we know that every year these automobile companies are just producing the new features of the car. So, how the new features are there? The main thing is they are just trying to put the new materials, or just they just want to refine the existing material so that they can enhance some of the specific properties of that. So, the same thing is there in the vibration feature also, that when we are trying to see that we want to design certain things for a certain part of this, we can say this applications part, then again we need to see that what exactly the sensitivity features are there in selection of the damping part of the material, so that if any changes are there, it is not requiring too many changes in the existing part, or else we can say that how the sensitivity part is there, especially related to the mass and other stiffness matrices of the materials. So, in this part now, the second category, we are just again going to discuss about the design consideration in the material selection for suppression of vibration, but mainly on the design specifications. Because we know that the actual design of any mechanism which starts and ends with the various performance objectives or the criteria is requiring a specific specifications, so that without any failure the robustness of the mechanism or the machine will remain. And the the quantitative criteria which are eventually stated in terms of the quantitative design specifications, so that we can actually get the desired performance according to the design of machine or mechanism. So, these performance criteria, when we are talking in terms of the design specification, are simply fallen in three basic categories: the speed of response, the relative stability, and the resonances. Because the speed of response is simply addresses that what is the length of the time which is being required before the steady state is reached. Because we know that when the things are just under the dynamic consideration, the basic principle of dynamics is saying that there is always the transient nature prior to get the steady state, and this is one of the fundamental law of that. So, when we are just trying to design, say, for the steady state feature, we need to just critically design, or we need to keep the design specification for choosing the material selection for this transient feature. So, this transient feature requiring that how much is the available time of this transient feature prior to go to this steady state, and this time is basically coming under the speed of response. So, when we are trying to say that we are basically interested to locate this the speed of response. So, in the classical control theory, this is being measured in terms of the rise time. As you see, we are generally saying that this is the rise time, and then you see it is just coming to the steady state part, or even we can say it is a settling time or the bandwidth. So, in vibration analysis we can say the speed of response is being measured in terms of the decay rate or the logarithmic decrement for that. This is what the analogy feature in classical control theory and the vibration analysis. So, speed of response essentially indicates the length of time for which a structure or machine experiences the transient vibration. And we know that when we are just going for a generalized solution, generalized vibration problem, then there are, you see, the transient and the steady state solutions are there, and we need to check it out, the nature of transient feature, and you see how the variations are being there. So, it is the time which elapsed before the steady state responses are being dominated in the feature. So, you see here the speed of response is one of the significant criteria in selection of that, because you see here this is what needs to be addressed in their specification prior to go to the steady state response and the analysis are being carried out. So, if it is a single degree of freedom system, then the quantities are simply like we can say like just varied according to the specified orientation. But if we are just trying to go with these quantities for multi-degree of freedom system, then again we need to map these single degree of freedom system variation of individual quantity to entire degrees of freedom which are to be described for the multi-degree of freedom system. Say we have the nth degree of freedom system with a position vector q, then the q equals to q1 of t, q2 of t up to qnth of t with the transpose. So, any property can be there, maybe force, displacement, anything is there, you see the linear displacement, angular displacement and all. So, if one force is applied say to the mass m1 and one displacement is there in the single degree of freedom system say q1t, then the specifications for the speed of response of q1t can be defined easily. How? Now, there is a procedure for that you see here the settling time in this is the time required for the response q1 time to remain within plus minus alpha percentage of the steady state value of q1t. So, now you see what we are trying to set up the relation here in between, that steady state time will approach there, but prior to that how much time will be required for the settlement of the transient to the steady state, which we always try to put the plus minus alpha percentage of that. And sometimes you see alpha can be like varied right from 2, 3, 4, 5 whatever in that. Second is the rise time, because you see it is just starting from 0 and going up to the peak. So, the rise time is the time required for the response to go up to say 10 to 90% of its steady state value. So, these specifications with the settling and the rise time is simply pertain to the transient response of a single input single output configuration, so that we can straightway configure that you see these inputs are coming and they are in the transient nature, and you see what is the nature of the system input. Accordingly, you see like the transient features can be settled down with the with respect to the settling time and the rise time towards going to the steady state feature of that. But on the other hand, if the interest is in the total response of the system, say you see like just generalized solution, then the vector q can simply give the response bounded towards the method of quantifying, which needs to be decaying, which needs to be consisting of the decay rate of the system. So, we can say in particular that a decay rate can also be straightway considered as q of t, the modulus is always being less than whatever the matrix phenomena m is there into e to the power minus beta t, where we can say that it is always being satisfied for all the values in the preceding part t greater than 0. So, that can be specified in terms of the time constant, and that you see it is always being required when the beta is equals to 0, we can get the time constant as t equals to 1 by beta, because it is what you see the exponential carrier e to the power minus beta t. So, you see we can straightway show the sensitivity of this beta in by taking one example. Say we have a system response with the position, and the first component of this vector position x of t is the q of t equals to 1 minus e to the power minus t into e to the power minus t. So we can say that now it is absolutely bounded by the e to the power minus t minus e to the power minus 2t is less than the e to the power minus t modulus. We are considering here b equals to 1 and decay rate is also 1 there. So in some situations the relative stability of the system can also be quantified, in particular that what the system is to be designed to be stable or asymptotically be stable can also not not giving the significant solution in that way. So here we are saying that you see that how the exponential decay is being featured out and how we can simply get the decay rate in this case. So like when we are talking about like the asymptotically stable or the stable feature, it is especially true when some of the parameter of the system may change over the period of time, or even they are changing owing to the manufacturing tolerances if the system is under any kind of active control. So when we are talking about the second factor, stability, we know that the concept of stability marginally used to quantify the relative stability of the system with respect to the surroundings. So now like the various systems are there which are simply showing the stable or become unstable when the parameters are being changes, even like the slightly featured out, the slight changes are being featured out, and that can be straightway carried out in this way. So for the system in which the single parameter is being used to characterize the stability behavior of the system, then we are taking the stability margin SM of the system, which is nothing but equals to the ratio of maximum stable value of the parameter to the actual value for the given design configuration. So here we need to check it out that what is the stable value for that system is first with the maximum, and what is the actual value incorporated for that kind of changes. So now you see here we can take some of the example for this. Say you see we have a system which simply defines, say gamma equals to 1, C1 and C2 are there, and we just want to calculate the stable margin of the system as the parameter changes. And we are considering here that one design parameter, say this neta is there. So as the design parameter neta is increasing, the system is approaching towards unstable feature, and say you see our operating value neta, which is being their optimum part, say 0.1, then we need to go towards the stiffness matrices, and we can simply find out that the stiffness matrices become semi-definite for all n equals to 1, and they are indefinite when this design parameter is greater than 1. So we can say it is the maximum stable value for neta is neta maximum equals to 1, because we just want to go with the stiffness matrix variation when the design parameter is to be calculated, as we discussed in the last lecture. So with this concept we can say that the stability margin with this consideration of the neta is nothing but equals to the stable SM equals to neta maximum divided by neta optimum. We have 0.1 divided by 1, which is the maximum like the neta, divided by optimum part is 0.1, which is equals to 10. And if the design of the structure is such that we have the optimum neta, the parameter, the sensitive parameter is 0.5, then certainly the stability margin is 2. So we can say that for all the vectors which become equal with this particular specific design, then the design with optimum neta 0.1 is more stable than the same design with the neta optimum 0.5, because when you have the neta optimum you see like a 0.1, then the stability margin is quite more 10 as compared to the stability margin with 0.5 is 2. So from this you see here we could easily signify that what exactly the impact of this design parameter with the specification feature, so that we can get the stability towards the entire system when we are changing this part. So this was the second, and the third was the resonance. The resonance properties or the modal properties of the system are obviously you see like coming under the design criteria in the sense that it is most like we can say circumstances resonance is to be avoided. Either it is the entire system resonances or even within the like the materials resonances, because we know that when the entire material is under like the resonant condition, the intermolecular interactions are under the severe oscillating feature, and sometimes even instead of like absorbing the energy with the material damping, the damping is just providing the energy to the system, which make the system unstable. So, the resonance is one of the significant criteria which needs to be avoided by any way. Various, you see, we need to apply the various ways to that towards that. So, the natural frequencies, mode shape and the modal damping ratios are often specified in the design work. So, whenever you see we are designing any system, we need to check what exactly the natural frequencies which needs to be considered according to the degrees of freedom, what are the corresponding mode shapes with these natural frequencies, because you see through that we just want to check it out the relative displacements, and you see how the variations are there in the modal damping ratios with this. So, now you see here when we are talking about this, now our main focus is on the modal reduction, because sometimes you see when we are taking the many degrees of freedom system, then it is not easy to find out, you see, the entire natural frequencies and the corresponding mode shapes and the modal these features are there in that, the damping features. So, a difficulty with many design and the control methods are always, you see here, like we can say problematic when we are going for the multi degree of freedom system. So, we can simply choose a small degrees of freedom system, and then we can effectively apply the control methods and the strategies. Through that, you see here we can effectively apply all that control path. But many interesting problem always having, interesting problem means the real application features of that is always having the large structure with many degrees of freedom system. So, here we are going to say that how do we do that. So, one of the specific thing is the modal reduction, because there is always a dilemma to reduce the size of the original model by essentially removing those part of the model that affect the dynamic response of the interest. So, when we are trying to reduce the variation in that by not affecting the dynamic response of the entire structure, this process is called the modal reduction, or we can say we need to reduce the order of the formation of the entire system modeling. So, it is quite often that you see the mass matrix is always we are considering the singular feature or near singular owing to some element being much of the smaller than the other. So, it has to be symmetrical way, it has to be singular feature. But in fact, in some cases, like you see when we are doing this finite element modeling or something, the mass matrix may contain the 0 along the portion of the diagonal part. So, that means you see here the mass matrix is inconsistent along the diagonal feature, or we can say you see sometimes we need to check it out that why the variations are being coming out in the mass matrices, how to do this particular the singular or just closely singular mass matrices. And the coordinates which are associated with the 0 or relatively small masses are likely candidates for being removed from the model, and through that we can simply go towards the reduction of the model. Another set of coordinates that are likely in choices for removal of these model are those which are not responding actively when the system is being excited. So, here we can simply check that you see these are some of the damp features which are not even coming and contributing in not only in the natural frequency, but also in the eigenvectors when the system is under exciting feature from the mass. Or else you see we can say that some of the coordinates which are even having more significant responses than other. So, we can consider the undamped force vibration, say x of t is nothing but equals to u of z t, in which you see the partition of the mass and the stiffness matrices are can be straightway configured with the significant displacement, and we can simply put the displacement q of I or q of t according to the two features there. So what does it means that now we are trying to see that what are the significant responses in this, and in that you see here we can now check the two types of displacement under the excitation of undamped forced vibration. One is the significant displacement, say we are saying Q1, and one is the insignificant displacement, say Q2. So when we have these things, now we are trying to model the equations of motion based on that. So we have now say that the M11, M12, M21 and M22 are the basic mass matrix elements, and when they are trying to relate with the Q1 double dot and Q2 double dot, and the corresponding you see like for undamped system the stiffness matrices are coming with Q1 and Q2, then we can say that the coordinates which are being like arranged in this fashion can also be rearranged in such a way that they can simply give the least significant displacement associated with that. So we can say that the partition displacement vector Q of t is nothing but equals to Q1 transpose and Q2 transpose, and then you see we can consider the potential energy of the system, which is nothing but you see like the scalar quantity V of E is nothing but equals to this whatever the changes are there in Q of t, which we discussed previously, that how the positioned displacement vectors are there. So it is Q of t into KQ divided by 2, or we can say that we can simply get the potential energy in form of the matrices. So this is nothing but equals to half Q1 by Q2 transpose the stiffness matrix Q, KQ is K11, K12, K21 and K22 with the corresponding displacement Q1 and Q2. So this is one energy which is being available with the variation of the restoring forces with those elements, the stiffness. Like you see we can calculate the kinetic energy of the system, the TE, which is nothing but equals to half Q dot transpose into MQ dot. So we can calculate you see these things like half in the matrix form Q1 dot and Q2 dot transpose M11, M12, M21 and M22, Q1 dot and Q2 dot. So when we are just doing the partition in this particular form, then you see we can get both the potential energy and the kinetic energy in such a way that it can be straightway configured along with the stiffness matrix and the mass matrices, and in this each coordinate of Qi is acted upon by the forces Fi, because this is the forced forced vibration, and the condition that there is no force is to be there in the direction of insignificant coordinate Q2. So now you see here, now we are trying to configure those things where we have the significant coordinate, because we know that the significant coordinates are those where there is a direct application of force. The insignificant coordinates where you see the force applications are not directly involved, so that you see here they are not putting their contribution towards the excitation features in terms of natural or the eigenvalues, or you see the eigenvectors in that way. So now you see we can get this, the dVe by dQ2, because you see this variation is insignificant, is 0, and that you simply gives that the partial derivative del by del Qt of the Q transpose K11 Q1 plus Q1 transpose T K12 Q2 plus Q2 transpose K21 and Q2 transpose K22 Q2 becomes 0 when we are trying to resolve the matrix elements along with that deviation. And if you if we are solving the equations, then certainly we have the constraint relations between the Q1 and Q2, as the Q2 is nothing but equals to K22 inverse K21 and Q1. Here we are simply saying that K12 and K21 transpose are almost same. So when we are trying to put that, now we have the Q2 which is nothing but equals to minus K22 inverse K21 and Q1, and this you see expression simply gives that a coordination transformation from all full coordinate system Q is to be reduced now towards the coordinate system Q1, and you see this is not like a similar simply based on the similarity of transformation, but this is a clear transformation which simply gives the reduction of the model. And if this transfer, we can say if transformation matrix P is there, then the P is nothing but equals to I0 minus K22 inverse and K21, as we have simply seen the previous case. So if you are saying that this Q, which is you see the full coordinate system, now can be substituted in the equation and can straightway put the expression in the multiplied by whatever you see the things are being there in P into transpose part. So now we have a new reduction order of the entire system with the consideration of full coordinate system Q, as because you see now we are trying to multiply with the P transpose as Q equals to PQ1. So the P of transpose M into P, the mass matrix into PQ1 double dot plus P transpose K P into Q1 equals to P transpose whatever the forces are there. So it is F1. So now you see we can simply calculate the P transpose into mass matrix into P, that you see now we have a clear feature in this, that it is like the P transpose MP is giving the variation in the mass matrix and the stiffness matrix in such a way that it is equals to M11 minus K21 transpose K22 K22 minus the inverse and M21. Again this M11 is the first element minus the transpose matrix of K21, inverse matrix of K22 and mass matrix M21 minus M12. So there is a symmetricity now in terms of M12 is coming. So the another matrix form is the K22 inverse and K21, and then plus K21 transpose K22 minus 1 as we discussed in the second term, and then it is you see here M12 and K22 inverse when you are multiplying with K21. So ultimately when we are trying to keep this in the mass matrices with the P transpose and P, we can also form the stiffness matrix with the P transpose K into P is nothing but equals to K11 minus K12 K22 inverse and M21. So this is what the reduction feature. The last expression is simply we can say commonly used to reduce the order of vibration problem in a such consistent manner that even in case of like the coordinate representation in which you see some inactive features are there, insignificant features are there, can be straightway reduced by eliminating the Q2 from that. And this can be greatly we can say adopt in various analysis problem in like this one. So if we are saying that if some of the masses in the system are just negligible or even the 0, then the formula again can be used by simply putting the reduction of like entire model feature of the vibration problem by putting the M22 equals to 0. So we need to say that this is something in which you see the mass matrices are being removed. It is called the mass condensation. So you see here the symmetric feature of the mass is being just eliminated in that. Now we are considering one example with the 4 degrees of freedom system, and in which the mass and stiffness matrices are being like that. So mass matrix is nothing but equals to 1 by 420, and all these elements are 312 along the diagonal, 312, 156, 8 and 4, and the respective other the elements of the matrices are like in the first row we can say the 312, 54, 0 and minus 13, second 54, 156, 12 and minus 22. Similarly for third and fourth rows are like that. So the diagonal is like this, and then you see we can simply go with the stiffness matrices for this 4 degrees of freedom system. We simply show 4 by 4 like the elements. So it is 24, 12, 2 and 4 along the diagonal, and then you see like corresponding things are there with this, say minus 12, 0, 6 and then minus 12, 12, minus 6, 6. So minus 6 in between is this one, and also for the fourth element 2, 4, 4, 4 like this is there. So this is a clear representation of the stiffness matrix with the symmetricity as it is being required for the system with the 4 degrees of freedom system. So now you see here when we are now trying to remove the effect of these last 2 parameters because we want to reduce this one. So what we are doing here, we are simply making now the sub matrices of the equations so that we can easily identify that what are the critical parameters which can be put into the significant or insignificant criteria. So when we are saying the mass matrix M11, so certainly it is 1 by 40, the first element, that is 312, the first like we can say array 312 54 54 156. Similarly, we can go with the subset of M12, that is nothing but equals to 1 by 420, 0 minus 13 13 minus 22, and similarly we can go with the M22 as well, which is nothing but showing this the entire element in between 140 1 by 420 8 minus 3 minus 3 4. So you see here, this is what it is. We can go with this. This is what my M33 was there, you see here, and accordingly we can choose this and we can choose this with dividation of 1 by 20. So one either M11, M12 or M33, like you see, this can be straightway calculate according to the requirement of this. So we can simply go with M11, M12 or M22 in this way. Similarly, the stiffness matrix, the K22 was nothing but equals to, like if you just go the 2 4 and 4 4 like that, you see. So 2 4 and 4 4, the last element, as I discussed in this, that this is what my K22, and then you see I can calculate the K11 with the first part as 24 minus 12 minus 12, 12 is this 12 is there, that is my K11, and K12 can be straightway calculate 12 minus 6 and 2. So this is what you see here, it can be straightway putting here, and we can get the transpose of, you see, this one. So K12, which is nothing but this element, is the K21 transpose feature. So these two last matrices are simply showing the resulting feature of the reduced model, the reduced order model of the structure. So we can say now we can go with the two main part, the P transpose mass into P matrix, which is simply giving now when we are trying to multiply this with this is 1.012, 0.198, 0.198 and 0.236. At the same time we can calculate the P transpose K and P, which is giving the 9333 like that. So these are, you see, like the two main, we can say the reduced order model, this entire matrices are there, which are clearly showing that how the reductions can be done with the significant and insignificant features of that. So now if you are comparing the eigenvalues of the full order system with those with the reduced order system, we can see that, you see, there is a clear transformation feature, the P matrix transformation matrix P can be used to perform the reduction, which is not, again you see, like the similarity transformation, and then we cannot go that, you see here, whatever the like the preserved value of the eigenvalues are there, we can straightway use and we can simply transfer based on the similarity transformation. So here the eigenvalues of the reduced system and the full systems can be straightway compared like this. We have the lambda 1 Rome, which is 6.981, and the lambda 2 Rome, whatever you see, like this feature is 12.916. And similarly, you see here, when we are trying to put this, we have now the lambda 3 and lambda 4 for this kind of the feature. So when this is the reduced order model, Rome is the reduced order model, you can simply see that there is a clear feature that you see we have the 3.83 into e to the power 10 to the power 3 and 230.934 is my lambda 3 and lambda 4 in comparison to the full scale model. So there is a clear feature that you see here when we are trying to find out the eigenvalues of the reduced order model and the full model, there is a clear comparison that you see we can get, you see, the lambda 1 and lambda 2, lambda 3 and lambda 4 in such a corresponding way that it can be easily replaced with this. So as I told you, the Rome refers to the reduced order model, and in this case you see the reduced order model captures the nature of the first two eigenvalues very easily. There is no a problem in calculation the significant features of that. But you see this is not always the case, because you see the transformation matrix P is always been defined by the this by consideration the Guyan reduction. So unlike the matrix P from the model analysis, it cannot preserve the eigenvalue problems, as just like in the similarity transformation they are always preserving, you see, the eigenvalues of the eigenvalues of the system this property with the full system analysis. So here in this case you see we need to check it out that how much preservance is there of the real eigenvalues of the full system. So, when we are applying in the model reduction system, means in which you see like there is a reduction of the model parametric feature, then we need to check it out that what exactly the compatibility is there in between that, and accordingly, because this is Guyan reduction for formation of this transformation matrix is always being considered in such a way that it should be compatible, and whatever the values, the eigenvalues are coming, though you see it gives you a clear and easy part of this eigenvalues, but it needs to be preserved in such a way that there should not be significant change in this. So, in this design specification feature of like the material consideration, today we discussed about mainly the three main part of that, the speed response, because the speed of response is clearly showing the dependence of the entire responses on the transient to the steady state in between that. And second was that when you are like checking this, what is the stability feature of that, because the specifications can be changed of the material for suppression of the vibration, but it should not like allow the system to go in the unstable manner, just like you see in the speed of response. When we are changing the specification, we are not trying to allow those to go, you see here like the transient feature becomes more dominant as compared to the steady state. And the third was the resonance. So, when we are trying to refer the resonances, we need to check it out that whatever the specifications are being changed or the modification, then what is the criteria to avoid the situation of the resonance. So, these things were discussed in that, and then we discussed about how to reduce the model, because ultimately in the specification, when we are going for the material considerations and when you have a multi-degree of freedom system, then it is not that easy to find you see entire things and the changes in the multi-degrees of freedom systems. So, then we need to reduce the order of the model, and then we can straightway apply the sensitivity in those things where the significant features are there, either in the mass or the stiffness matrices in that. So, in the next lecture also we are going to discuss about the design consideration of the material selection, and we will try to focus on other like issues, so that when we are trying to design the material for reduction of the vibration, then we can simply configure those properties, and we can simply put you see these orientations towards the designing feature of the materials.